So our double angle formulas are just kind of these short little identities that come from those sum and difference identities that we just did in the previous video. So you can literally get them from the sum and difference formulas, but they're so useful that they're actually good to kind of memorize on their own. So for example, let's suppose I wanted the sine of 2 times theta, double theta. Well, that's like saying the sine of theta plus theta. Well, based on our sum formula for sine, that's the sine of theta cosine theta plus sine of theta cosine theta. They'd all be the same, so that would be 2 sine theta cosine theta. This is an incredibly useful formula as you progress into Calc 1, Calc 2. And it takes away the double theta. And it says that sine of 2 theta is equal to 2 times sine theta cosine theta. An incredibly useful identity that just comes from that sum of sines. Okay, very useful. We can do the exact same thing with cosine. Cosine ends up being a little trickier. Oh, not really trickier. So here you can see cosine of, say, theta plus theta is now, if we go back to our cosine, it's cosine theta minus, because remember cosine, if it was a sum, you end up with minus in the identity, sine theta, which is cosine squared theta minus sine squared theta. So we have cosine of 2 theta. Now, not quite used as often as sine 2 theta, but this is another one you come across, and you can change any cosine 2 theta into cosine squared theta minus sine squared theta. But using Pythagorean identity, we know that cosine squared theta plus sine squared theta equals 1. So cosine squared theta equals 1 minus sine squared theta. You can actually do variations of this one. And we can also say that cosine of 2 theta, and I'm going to replace cosine squared theta with 1 minus sine squared theta. And that's going to allow us to end up with, if you kind of do the math, you get 1 minus sine squared theta minus sine squared theta, so you get 1 minus 2 sine squared theta. And if I replace it the other way, meaning we know that sine squared theta would be 1 minus cosine squared theta, then another variation, replacing the sine squared theta, is going to give me cosine squared theta minus 1 plus cosine squared theta. That's going to give me 2 cosine squared theta minus 1. So here are 2 other variations that could be useful. So we have 1 for sine 2 theta, but we have 3 for cosine 2 theta. And the tan one, if you were to do the same thing, I'm just going to give that one to you. Tan 2 theta is 2 tan theta divided by 1 minus tan squared theta. So, okay, the video got cut off for a second. I apologize for that. Some news feed kept popping on. I had to fix that. Anyway, you know, these are kind of simple little formulas, but can come in handy. And of course, they can be used also to verify an identity. We'll go over one of those in a second, but let's just take a look at a more kind of simple problem that you will come across. So if you are given say sine theta equals 5 over 13. And, well, let's put it this way. Instead of saying that, let's say that theta is greater than 90 but less than 180 degrees. So that tells you right away that theta lies in the quadrant it lies in, which in this case will be quadrant 2. So that information tells you the quadrant. So you're sketching it, and all we know is that the sine of theta, it's in quadrant 2, and sine is 5 over 13. So what I wanted you can do is you can find different things based on that. You can find, for example, sine of 2 theta. Well, that's going to be 2 sine theta cosine theta. Well, we already know sine theta, it's 5 over 13. Cosine theta you do have to get from drawing that angle in the appropriate quadrant and finishing it with the Pythagorean theorem. That's going to give you this to be 12 because 169 minus 25, 144 squared root of 144 is 12. And be careful with your negative positive signs. That 12, because we are in quadrant 2, is negative. So cosine of theta then becomes negative 12 over 13. Keeping in mind that is your theta, and we are using its reference angle to get those. And then we would simply, the answer is going to be negative 13 times 13 is 169, 10. So it looks like 120, right? 2 times 5 is 10, 10 times 12, 120. Negative 120 over 169. Okay, you can get the sign, you can get any double angle that way. But as I stated, you can also verify identity. So when do you know you need to use these when verifying an identity? So here's one, cosine this one's a little bit more. You got to figure some things out a little bit. Let's prove that cosine 3 theta equals 4 cosine cubed theta minus 3 cosine theta. Now, I know we did not do any triple angle identities, but we can take a look at our sum and difference and our double angle identity to use this. Now, how do I know I've got to use those? Well, number one, you don't have a formula for a triple angle for 3 theta. But we do have a formula for 2 theta. And we also have a formula of cosine and 2 angles together. So can I do 2 theta plus theta? And see if that gets us somewhere. Because you have an identity that deals with the 2 theta, and you have an identity that deals with the sum of angles and taking the cosine of that. So let's go ahead and take the cosine of 2 theta plus theta. This will get us back into our last video. We had to do the sum of cosine. So we have cosine 2 theta times cosine. Remember, cosine keeps them kind of together. Then you subtract, because it's a cosine, sine 2 theta, sine theta. All right, well, that's nowhere near what we have on the right-hand side. So we're going to keep working down this left-hand side. Now, here's the good thing. We have formulas for cosine 2 theta. And we can take that because notice, here's what I want you to notice on the right-hand side. Everything's just a theta. There's no 2 theta, 3 theta, so we've got to get rid of this coefficient of theta. 3 theta we got rid of by turning it to 2 theta plus theta. 2 theta, I'm now going to use identities. Now, you can use different ones. I know we have options for cosine 2 theta. Look, cosine squared minus sine squared, 1 minus sine squared. So here's what I want you to notice about these options. The first one has a cosine and a sine in it. The second one just has a sine squared, and the third one just has a cosine squared. Well, if you kind of use your right-hand side here as a guide, you're like, okay, well, I got to turn everything into cosine, so I don't want to introduce a sine in this first part. Since I want to keep it as cosines, I'm going to take cosine 2 theta and turn that into cosine squared minus 1 times cosine theta. Now, sine 2 theta, I only have one thing. 2 sine theta cosine theta. And then you can multiply by sine theta. So here's what I'm saying. I'm trying to get this first piece to kind of look like this first piece. Let's see if that works. I'm going to distribute across. So now I have cosine theta times, well, that's 2 cosine cubed theta. Well, I'm getting closer. Minus cosine theta. And then I'm going to come over here and distribute. That's 2 sine squared, not distribute, I'm just going to multiply actually. There is no distributing. Cosine theta. Okay, well, keep an eye, always be looking at what your goal is. And our goal on that right-hand side of that identity only has cosines in it. So what I'm going to do is take that sine squared theta and say, hey, wait, I know a way to change sine squared into 1 minus cosine squared times cosine theta. All right, I'm getting closer. Let me just distribute again. Sorry, my battery's starting to run out and I don't want to lose it before I finish this problem. So I have cosine times 2 times 1 is 2 sorry, that's not equals, that's minus. And then I have cosine times minus 2 times minus, that's plus 2 cosine cubed theta. That goes with that to give me 4 cosine cubed theta minus 3 cosine theta. There it is. Which equals my 4 cosine cubed theta minus 3 cosine theta. So there's a nice little identity that used. Don't forget to write it in as you used it. This was the sum identity for cosines. And then I did the double angle for cosine and sine. I had to do one of each. And then I used the Pythagorean identity over here, and I got it to look like the other side of my equation. Okay? You're not going to do a lot with these double angles, but I will tell you they really come in handy as you progress into calculus.